Hello and welcome students. So till now we have discussed the basics of fault modeling, and I also covered in the last lecture about the concept of fault modeling in case of the combinational circuits. So you can consider that as a part 1, because in today's lecture I am going to cover some of the examples so that you can better understand that how we can actually model the faults in case of the combinational circuits. So treat this lecture as a part 2 in continuation with the previous lecture. Okay. So there can be two types of basic level where we can model the faults for the combinational circuit or any circuit. That is, first is the functional level fault model. So what we when we write functional level fault model, what is the basic meaning behind that? So let us understand. Circuit is specified at the register transfer level, that is, netlist of functional blocks like register, adders, multiplexers, etc. So fault models, those we are now, we are taking as an example of functional fault model. So in case of functional fault model, we consider the blocks. Suppose register as a block, multiplexer as a block, adder as a block. We are not going into the details of gates. We are not going into the details of the structure. So when we call the functionality, it means, suppose I am taking the example of multiplexer, then it can be 2:1 or 4:1. So we will check about the functionality of the multiplexer. We are not going inside the multiplexer to check what structure it is having. Okay. So fault models, which are based on the function of the particular block, it is known as the functional level fault model. So fault models are block specific and not general. This means that here I have written, it means suppose you are designing the fault model for an adder, then the same model cannot be applied to multiplexer and so on. It is very simple to understand because the functionality of the adder is not similar with the subtractor, or is not similar with the any other decoder, encoder, or multiplexer. So each time when you are designing the functional level fault model, there has to be difference between the models so that you can efficiently test the faults for that particular combinational circuit. So let us take an example of a 4:1 multiplexer here. So this is the multiplexer. This is A0, A1, A2, A3. Four inputs are there, and these are the select lines S0, S1, and this is the output F. So now look at this particular truth table here. A0, A1, A2, A3, S0, S1. So when S0, S1, 0, 0, this A0 is going to be selected. So how it is going to be selected? Suppose I am applying 0, 0, then this 0 is coming as output as a Q, and then for next output, next input, sorry, if I am applying input as a 1, then it is coming in as a 1. So when I am applying 0, 0 as a select line, it is going to select the input A0, and that A0 will propagate at the Q. 1 as a, at one time it will be 0, and another time it will be 1. And then if I say 0, 1, 0, 1, S1, S1 is 0 and S0 is 1. So for 1, 0 it is selecting A1. For 1, 0 it is selecting A1, and similarly for next for the next set of cycles 0, 1 and 0, 1, it will select A2, and for next 1, 1, 1, 1, it will select A3. So at one time it will select A1, A0, then A1, then A2, and A3. Okay, so fault model here can be understood as for each input we are applying reverse logic at others, so that if any faults is there, it will be detected. So how we can model the fault here? How we can model the fault here? Look at here. Here A0 is 0. I am explaining the meaning of this particular line that I just told you. A0 is 0. Now you are applying reverse logic at A1, A2, and A3. Similarly, here A0 is 1. Now you are applying the reverse logic as 0, 0, 0 here. So when you are generating the test vector, how you are doing? you are just applying the reverse logic so that whenever there will be any fault, this fault will be detected at the output. Okay, so here if I want to check for A0 whether it is faulty or not, I have applied 111 at the other inputs. So whenever this become 1, the fault will be detected. What we studied in the previous lecture? In previous lecture, I told you that there is exclusive OR condition between the fault-free circuit and the faulty circuit. Fault-free circuit is the one which is having no fault. Faulty circuit is the one which is having some kind of fault. So if you are taking the exclusive OR between these two, you will definitely get an output. So that output is nothing but the difference between the fault-free circuit and the faulty circuit. Okay, so similarly, what I am doing here, suppose this is 1 and I am applying 0, 0, 0 at the other inputs. Okay, so whenever it becomes 0, there will be an output which will tell me that there is error in case of A0 or at line of A0 and so on. So to test this particular 4 input multiplexer, how many test vectors are required? If we go by this truth table, this is first test vector, this is second test vector, this is third, fourth, fifth, sixth, 7 and 8. How many test vectors required? 8 test vectors are required to test this particular multiplexer. And now if you go by the binary logic, how many inputs are here? This is 4 inputs and this is 2 as a select line, so 6 inputs are here. So if you go by the binary logic, you will need 2 to the power 6 equals to 64 kind of combination if you go by individually checking the inputs and taking 0 1 0 1 0 1 as the testing sequence. So this particular model of multiplexer can be, checked by applying just the 8 test vectors in comparison with the logic. Here, if we go by the inputs, then we have to apply 64 different test patterns. Okay, so this is how, this is example. This is just an example to tell you that how the idea of fault modeling is there in case of the digital circuits. Okay, let's move ahead and see some other concepts. Structural level fault model. As I told you in previous case, we were talking about the functional level fault model. Now in case of the structural level fault model, circuit is specified as a netlist, typically at the level of gates and flip-flops. So I told you in the previous case that when I am taking functional level fault model, then I am addressing the individual blocks in the combinational circuit. I am talking about multiplexer, adder, subtractor individually. And if I am taking the structural level fault model, then I am going inside that particular adder or multiplexer, and I am seeing that whether there is a fault in the structure of the multiplexer or structure of that particular block. Okay, so some important assumptions are there in case of the structural level model. First assumption is the blocks are fault free. So here, what is the meaning of the block? Here the meaning of the block is gates. Suppose you are designing a multiplexer. So multiplexer, if you are designing the multiplexer, inside the multiplexer there can be, I mean, 3 gates or 4 gates or 5 gates, combination of AND or OR gate. That can be, I'm not going into detail of the multiplexer design. I'm just telling you here the block means the number of gates. Let us say AND gate or OR gate or NOR gate or NAND gate. So we are assuming that the blocks are fault free. Then where the fault lies? The interconnection between blocks can be faulty. It means, suppose you are connecting one AND gate to another AND gate, and that AND gate is connected to another OR gate. So whatever interconnection these gates are sharing, there can be a fault in that interconnection. And what that fault can be is stuck at 0 and stuck at 1. We abbreviate it as SA0 and SA1. I have already told you in previous 2 lectures what is the fault SA0 and SA1. Now we try to understand this. Some the other important aspects of this fault model. Fan out stems and fan out branches are considered as separate lines. This is important to understand. What is fan out stem and what is fan out branch? Let us take an example. This is an AND gate. Two inputs are here. Two input AND gate is shown over here. A and B is the input and F is the output. This is known as the fan out stem, because it is feeding other two outputs, F1 and F2. So these are the fan out branches. Suppose there is a fault here known as stuck at zero fault. There is a fault here known as stuck at zero fault. Because this fault is here over the fan out stem, it will definitely affect the logic of F1 and F2. Okay, and suppose this F1 is connected to some other AND gate, then this F2 is also connected to some other AND gate. And if there is a fault at this line known as a SA0 or stuck at 0, then the fault over here will not affect the fault over here, or I would say that fault over here will not affect this line as well as this line also. So what does it mean? What does it mean? So fault at the fan out stem will also affect the F1, F2, as I told you, first case and second, but fault at F1 only will affect the, it will not affect the F and F2. Okay, I hope you have got the logic. So this fault can affect the logic of F1 and F2, but here this fault cannot go back and affect the fault of the line at F or F2. So fan out stem and fan out branches are different in case of the fault model. This is very important to understand. Now single stuck fault. So stuck fault can also be of two types: single stuck fault and multiple stuck fault. I have already told you this particular logic as well in the previous two classes, that if it is not given in your problem or in your circuit, or if nobody asks you that whether your circuit is having single stuck fault or multiple stuck fault, always assume that your circuit is having the single stuck fault model, the single stuck fault only. Why I already told you? Because we are having the efficient testing methodology, and the testing period, or the frequency of the testing is such that at every next stand or at every next cycle we are going to test the faults. So generally what designers or what testers or the testing designer or engineers assume that the single stuck fault is there in case of the circuit, because the number of frequency to test that particular circuit increases every time. Okay, so the fault of the idea of, or the concept of multiple stuck model is, we can say that it is out of the picture. Okay, so let us understand single stuck fault model. Only one line of the circuit has a stuck fault at any given time. Already told you that. Most widely used fault model in the industry. Okay, and next, for a circuit with k lines, total number of single stuck faults is 2k, twice of the lines. Let us understand this circuit. Here it is a NAND gate, NAND gate, NAND gate, NAND gate. It is nothing but a representation of XOR gate in terms of the NAND gate. And here you can say how many lines are there. This is the first line, this is the second line, this is the third line, this is the fourth one, fifth one, sixth one, 7, 8, 9, 10, 11, 12. So 12 interconnection lines are there where we can have faults. Either it can be stuck at 0 or it can be stuck at 1. So 12 lines are there and fault types can be 2. Either it is stuck at 0 or stuck at 1. So 12 multiplied by 2, then you can say that this particular circuit can have 24 number of faults. Okay, so this is how stuck at fault model is done. Now, if we switch to the multiple stuck at fault, for a circuit with k lines, total number of multiple stuck at faults is 3 to the power k minus 1. Now, where this 3 is coming out, k is nothing but the lines that we have already seen in case of the above circuit. Here the number of lines are 12. So I'm taking the same example. Now, if I am assuming that the circuit is having multiple kinds of fault, multiple stuck at faults are there, then how we can calculate the actual number? So what is the three possibilities are there. The fault can be stuck at 0, the fault can be stuck at 1, or there can be no fault. So there are three possibilities. We are assuming the multiple fault case now. So it can be fault free also, it can be stuck at 0 also, or it can be stuck at 1 also. That is why these three is written over here, and this 12 is nothing but the lines that is holding, that can hold the fault. So 3 to the power 12, and why it is minus 1, why we are taking that minus 1, because there is one combination at least that will be fault free. So 3 to the power 12 minus 1, it's coming out to be 5,31,440. so can you test these number of faults? It is impractical, and that is why the multiple stacked fault model is not popular at all. Okay, so let us also understand some examples, and so that I will tell you how to decide the test vectors, and how test vectors actually help you to test that particular gate, or I would say the block that you are going to apply the test model at. And it is very important with that prospect also, because we are going to see the test pattern generation for the combinational circuit, that how we can generate the test patterns. So it is important to understand that how test vectors are actually applied over the circuit, so that you can understand that how we will design the, or how we will decide the test pattern of that particular gate. So here this is two input AND gate again. So three test vectors can decide, or can test this particular AND gate. What are they? 0 1 1 0 1 1. So let us understand one by one. Suppose you are applying 0 1, so it is 0, A is at 0 and B is at 1. So it can detect A is stuck at 1 and F is stuck at 1. How it can detect? Let us understand. Suppose you are applying 0 and 1. So 0 and 1 will give you output as 0. 0 and 1 will give you the output as 0. So if there may be fault at, or there will be fault at A, suppose it will come out as 1. And what logic we are applying here? We are applying here 0. Suppose it will stuck at 1. Stuck at 1, fault is there. So what will be the output? Output will be 1. Now what is the output? Output is 0. So there can be XORing condition. The original output is here 0 1 is 0, and if there is stuck at 1 fault here, then 1 1 will be 1. So that 0 will XOR with 1, and you will get as a difference as 1. So it can detect stuck at 1 fault at line A. Similarly, if the F is stuck at 1, we can also detect that fault with this particular logic. Why? Because if we apply 0 and 1 here, it will come out as 0. And if F is stuck at 1, then we can easily say that the original output is 0, and now since the F is stuck at 1, so again the exclusive OR condition will come out as true, and we can say that there is a difference between original idea, that the original output, and the faulty output. Similarly, you can apply the test pattern 1 0 here. So if it is 1, it is 0. It is 1 and it is 0, then also the output will be 0. So where we can detect the fault now? We can detect the fault now at stuck at 1 at B. Okay, and similarly F at 1. F is stuck at 1. Okay, and if we apply the test vector as 1 1, suppose this is 1 and this is 1, then which fault we can detect? We can detect all the stuck at 0 faults. A is stuck at 0, B is stuck at 0, and F is stuck at 0. How we can say that? Suppose if I'm applying here 1, if I'm applying here 1, then 1 1 will give me the output as 1. So either of the input, either A or either B will become 0, you will get the output as 0. So you can test the stuck at 0 fault. Similarly, if F will stuck at 0, then also you can detect the output stuck at 0. So this is how these three vectors are sufficient to detect all the faults of this particular AND gate. So this is how we decide the test vectors. So this is a 4 input AND gate, and this is the output. And by applying these test vectors, we can check, or we can test these particular AND gate with the 4 input. So you can go through all the steps and check that whether these test vectors are sufficient enough to test this particular AND gate. Let me give you one brief example. 0 triple 1. Suppose I am applying 0 here at A and 1 1 1 at all places. Since this is the AND gate, it will give as the output 0, original output as 0. And suppose if by any fault or by any means this A will stuck at 1, so your output will be 1 because other three lines are at 1. So what fault we can detect? We can detect A is stuck at 1. Similarly, the original model, the original out circuit will give the output as 0 because of this sequence. And if F is stuck at 1, again we can test that, or again we can say that the original output is not matching with the faulty output, so we can detect the fault over here. Okay, so you can similarly test the other patterns also, and by using these 5 test vectors we can again yeah, can test this particular AND gate with 4 input. Now here we will talk about the XOR gate. So XOR gate, you can say this is a 3 input XOR gate, and 2 test vectors, only 2 test vectors are sufficient to this to test this particular 3 input XOR gate. And how it is? Suppose we apply 0 0 0 here. So 0 0 will detect all input stuck at one faults and also output stuck at one fault. How? Suppose I apply 0 0 0 here, so it will give output as 1 because this is the XOR gate. Okay, so if there is any stuck at one fault, whether it is at A, whether it is at B, or whether it is at C, your output will become 0, is it not? So you can say that all stuck at one fault can be tested by applying the logic 0, and similarly the F at stuck at 1 can also be tested. You can apply the logic I have already explained in the previous 2 cases. Okay, and here suppose the 4 inputs are here. So 4 input XOR is here. This is the 3 input XOR. This is the the earlier case was the 3 input XOR, and now we are taking the 4 input XOR. This is the odd input and this is the even input. So for even input cases, one additional test pattern will be needed. How? Suppose all 0 0 0 0 0 will select all stuck at 1 at input and also stuck at 1 at output, that we have already seen here. Now if we apply 1 1 1 1 1 1 1 1 1, then you can say all stuck at 0 fault at the input can be detected, and stuck at 1 at the output can be detected. Okay, but what about if F will be stuck at 0? If F will be stuck at 0, then you have to apply this particular pattern 0 1 1 1. So if F will stuck at 0, you can say that 0 1 1 will give you the output as 1. So this 0 1 1 1 is not the only combination. You can also say 1 0 1 1. You can also say 1 1 0 1, or you can also say triple 1 0. Means any of the input should be 0 to test the stuck at 0 at the output. Any confusion is there? Stuck at 0, means F will be always 0. So these two test vectors cannot detect F will always, if F is always stuck at 0. You need to apply any of the input as 0, because if you apply any of the input at 0, then F will become 1, and then you can check the original output as 1 and the faulty output as 0. So 1 and 0, again the XOR condition will true, and you will say that your circuit is faulty, or your AND gate is faulty, OR gate is faulty, anything, whatever maybe the circuit is. So the in case of the XOR, if M is odd, you will need 2 test pattern, and if M is even, you will need 3 test pattern. So this is 2 test pattern 0 0 0 1 1 1, and these are the 3 test patterns. So reduction of number of test vectors, what does it mean? If you have 100 input XOR circuit, if you have 100 input XOR circuit, just by having the 2 test vectors, you can check that particular 100 input XOR circuit. And if the inputs are odd, suppose there are 101 faults are there in case of the XOR circuit, sorry, 101 inputs are there in case of the XOR circuit, then you will need another test vector, that is 3 test vectors. So by applying the 2 test vector in case of the even and by applying the 3 test vector in case of the odd, we can, you know, uh, go for the testing of n number of inputs and number of faults in case of the XOR gate. So the reduction of number of test vectors is the very important fundamental to understand. Okay, now the next very important fundamental in case of the testing the combinational circuit is, or any circuit is sequential, in case of sequential also, how to reduce number of faults, how we can plan our fault model in such a manner that by using less test vectors or less test sequence we can detect the fault efficiently. This is the idea behind, basic fundamental behind. Now the first concept is fault equivalence. The first concept is fault equivalence. Let us see this example. This is the 2 input AND gate. This is the F. We want to see the stuck at 0 at A. If there is any fault at input A, F will always be 0. If B is stuck at 0, then also F will always be 0. And if F is stuck at 0, then also F will always be 0. These three cases are equivalent, is it not? Suppose this input A is connected to 0, your output will always be 0. Suppose this B is connected to 0 or stuck at 0, your output will always be 0. Suppose the output itself by some fault connected to 0, then also your output will always be 0. So all these stuck at faults, all these stuck at 0 faults are equivalent because they are giving the equivalent logic, FS0, FS0 and FS0 in all three cases. So if I select only this vector, that is A is stuck at 0, I need not to go for the 3 different testing vectors, or 3 different test vectors are not needed in this particular case. So this is known as fault equivalence. All these 3 fault cases or test vectors are equivalent to each other. So if I choose any one, let us say if I am choosing the A stuck at 0, I will always test, or I can always test that F at stuck at 0 fault. Okay, so and for test vector we can apply and test vector is, so for a test vector we can apply 1 1 1. So if I am having any of the fault, let us say if I'm having the fault at here or here or here, that will become 0, then your output will become 0. So you are applying test vector as 1 1 and you are getting output as 1. And if fault is there at A also or at B also, you will be getting the output as 0. Whether it becomes 0 or whether B becomes 0, you will get the output as 0. So this is the testing sequence. You are getting the output as 1, and if the fault is there, then you are getting the output as 0, 1 and 0, the exclusive OR condition, and then you can test all these stacked faults. Okay, so input is stuck at 0 and output is stuck at, so similarly by this logic we can decide the other logic also. For NAND gate, if input is stuck at 0 and output is stuck at 1, so this is similar. Similarly, if input is stuck at 1 and output is also stuck at 1 in case of the OR, we are talking about the equivalence. What we are talking about the case of the equivalence. Similarly, input is stuck at 1 and output is stuck at 0, we can go for testing of the NOR. Similarly, input is stuck at 0 or 1 and output is stuck at 1 or 0, we can test the NOT gate. Again, I am repeating, here I am talking about the fault equivalence. As in case of the AND gate, we have seen that these 3 faults are equivalent to each other. In case of the NAND gate, all input is stuck at 0 fault and output stuck at one fault is equivalent. Similarly, in case of the OR, all input stuck at one and output stuck at one is equivalent. So you need not to go for individual test vector design. You can select the fault equivalent design, as I have already told you. So this is the idea of fault collapsing. This is the idea of fault collapsing, how we can, reduce the number of fault. Very important fundamental to understand. So here you are seeing the larger a circuit where three AND gates, two OR gate and another AND gate is connected. Now here, as I already told you, that in case of the AND gate, this SA0 at one input, this SA0 at the another input, and this SA0 at the output. Three stuck at faults at zero. This stuck at zero, this input, stuck at zero, this input, and stuck at zero, this input. Just we have seen over here. This A is stuck at zero, B is stuck at zero, and F is stuck at zero. F is the output. Okay. So all these three faults are equivalent. So you don't need this SA0 and this SA0 because this SA0 is sufficient. Okay, similarly in here also this SA0, this SA0 are not needed, this SA0 is sufficient. Similarly here also this SA0 and this SA0 are not needed, this SA0 is sufficient. Any test vector is sufficient, any test any fault is sufficient to detect. If I can detect fault here, these two fault at here are not required. If I detect fault here, these two faults are not required. If I detect fault here, these two faults are not required. Similarly, in case of OR gate, just opposite to AND gate, SA1, 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 SA1 here. In case of the AND gate again, SA0, SA0. So all those things which are shown over here in the red color are not needed, that can be simply deleted, and only the rest of the fault model or rest of the faults we will consider. So this is known as fault collapsing. Okay, so what is the basic idea behind the fault collapsing? The fault collapsing tells us that if I am testing any particular logic of any combinational or sequential circuit, then I need not to go for all the faults that are there in the circuit. I can easily choose in between the fault equivalent, uh, you know, uh, fault equivalence. I can check for the fault equivalence, and depending upon the fault equivalence, I can decide whether I will test this fault or not, or what faults I can ignore. So this is the idea behind fault collapsing. Okay. The basic fundamental, I would say, if you have studied the digital electronics, then you might have studied about the basic characteristic of the AND gate and OR gate. AND gate is sensitive to zero. Any of the input, if of the AND gate is 0, then output will always be 0. And OR gate is sensitive to 1. Any of the input of the OR is 1, then your output will always be 1. So if you are designing the AND gate, then all the stuck at 0 faults are equivalent because it is sensitive to 0. And if you are designing the fault model for OR gate, then all stuck at one faults are equivalent because OR gate is sensitive to 1. It's simple fundamental to understand. Okay, apply this logic, think over it, and then you can easily understand. The last topic of this particular lecture is fault dominance. Okay, the second method to reduce the number of faults. I already told you about the first method, that is the fault equivalence. Second fundamental is fault dominance. If all tests for some fault Fi also detect another fault Fj, then Fj is said to dominate Fi, denoted as Fj dominates the Fi. If you are applying the fault model, and if you are taking it as Fi, and suppose the another fault is taken as Fj, so if all tests for some fault Fi also detect the another fault Fj, so if that test is detecting both the faults, then Fj is said to dominate the Fi. Okay, So now output stuck at 1 dominates input stuck at 1 in the AND gate. We will understand this, how we are taking the example. So for every such dominance relation, Fj dominates the Fi, we retain Fi and we will remove the Fj. So whatever fault is dominating, we will remove that dominated fault and we will take the other fault, that is the Fi. So here Fj is dominating Fi, I will remove the Fj and I will only take the Fi. This is known as the dominance fault collapsing. Okay, so if two faults dominate each other, they are equivalent. How we can see here. So here first set of fault I am assuming Fi is SA1 stuck at 1 fault in one of the input at gate, say A. So I am taking this A is stuck at 1. Now Fj is stuck at 1 fault in output of the gate, that is the AF is stuck at 1. So in case of Fi, what is the fault? A is stuck at 1 and I have to test that particular logic. Then what test vector I am applying? 0 1 1. What I am applying? 0 1 1. Other two inputs are 1. This input is originally 1. So if all the, sorry, not originally 1, the fault we are assuming here it is 1. So other two inputs are 1. This is the test vector. Let us apply the test vector. Let us apply the test vector, then you can understand. A is 0, B is 1 and C is 1. 0 1 1. What will be the output? F will be 0. And suppose this A is stuck at 1. So 1 1 1. What will be the output? F at 1. So there is XORing condition again. XORing condition will be true. The original output is not matching with the faulty output. So you can test Fi. Now if you are going to test the Fj, what is the Fj? Fault at this place is stuck at 1. This F is always stuck at 1. So you can apply number of test vector. You can make all 0. You can make any of the input 0. Okay, so here all 0, 0 0 1, 0 1 0, 0 1 1, 1 0 1, 1 0 1, 1 0 0, 1 1 0. All these test vectors are for the case of Fj. What is Fj? F is stuck at 1. So instead of applying all these test vectors, can I not apply 0 1 1 only? This is 0 1 1 and this is 0 1 1. These are two common things, 0 1 1 here and 0 1 1 here. 0 1 1 here can also detect the fault at F. So these two faults hence said to be equivalent in the sense that Fj is dominating the Fi in terms of the number of test vectors. So instead of selecting 1 2 3 4 5 6 7 test vectors, I will only choose one test vector, that is the Fi, and Fj is simply eliminated and simply it can be removed. Why we can remove this? Because by only applying 0 1 1 we can test both the faults, that is the Fi and that is the Fj, that is the stuck at 1 at A and stuck at 1 at F. We need not to apply all these test vectors. So this is the idea of fault dominance. Okay, so in this lecture I have covered the very basic fundamentals and I have taken some examples. So if you are directly coming to this lecture, I would suggest you to go through the previous two lectures and then come to this lecture to better understand the fundamentals and the examples that I have taken. So next lecture we will talk about the test pattern generation of the combinational circuit. Thank you for listening and watching.